Oh, what a great day in 1941. Just be alive, reading my book about graph theory. Huh. Wonder if I have any new ideas. Oh! Oh, what was that? I think I just came up with a new theory.
So Brooks got this idea of vertex color in his head, but he needs a proof to show the world. So after many hours of thinking, he finally came up with a proof.
Oh my god! I got the proof!
So before we go into the actual proofs of the Brooks theorem, we're actually going to give out some background concepts and definitions of the Brooks theorem to make everyone understand it better. So what the Brooks theorem really does is to indicate the relationship between the maximum degree number and the chromatic number of the graph. The chromatic number of a graph is the minimum number of colors needed to color the vertices of the graph. So here I kind of drew like a heart between the two things because they're in a relationship. So in this proof, we will use n as the maximum degree number of a graph and x parentheses g as the chromatic number of the graph. So the Brooks theorem states that for any connected undirected graph G with a maximum degree number n, the chromatic number of G is at most n. However, there's a little plot twist to this theorem when the graph G is a complete graph or an all-cycle graph. The chromatic number then becomes n plus 1. So here is a graph G that is an all-cycle graph. As you can see, there are 5 vertices with the maximum degree number of 2. Therefore, according to the Brooks theorem, the chromatic number will be n plus 1, which is 3. So here is an example of a graph G that is a complete graph. As you can see, there are 6 vertices, each with a maximum degree number of 5. Therefore, the chromatic number of the graph is n plus 1, making it 6. So up next, we're going to talk about cliques, which are also known as subgraphs. So there are subsets of vertices that are attached onto the undirected graph. So here we have an example of that. As you can see, the maximum degree number is 3, and the chromatic number is also 3. So right now I'm going to do a little bit of review and talk about the concept of a spanning tree. So a graph becomes the spanning tree when the removal of one more edge will cause the tree to be disconnected. And the edge removed will be called as the cut edge, and the involved vertices will be known as the cut vertex or the cut vertices. Up next is the definition of a block graph. So here is just a graph that is considered as a block. So basically, a block is just a connected graph which does not have any cut edge. So in this graph, you can't really find anything that can be removed and cause the graph to be completely disconnected. And I made a mistake spelling edges, and here's a smiley face, kinda sorta.
So what the greedy algorithm states that if we want to color each vertex, we want to do it in using the least number of colors possible. Since there's 6 vertices, we can use 6 colors possible, but we want to use the least amount that we can. So we start with a random vertex, let's say a black one, and then we see the 2 vertices that are connected directly with that. So we get a separate color, let's say green. And then the 2 vertices that are connected to the black are not connected to each other, so we can both color them green. And then we have another vertex that both connects to the both green, so we get a black again because we want to use the least number of colors possible, and black is not connected to black itself. And then we have to come up with a third color for that one because black and green are connected to that. And then in the last one, we have to use brown. We say that a graph is complete and connected if there exists a path that goes through all the vertices in a given graph. So connectivity talks about how if we remove one vertex, or if we remove those certain vertices that are cut vertices, then we won't have a connected graph again. And we count the connectivity with how each removing of each vertex affects the graph. So here we have a 2 connectivity because there are 2 cut edges, or not edges, but vertices. And let's say if we were to remove the bottom cut vertex, then remove its adjacent edges to it. So if we remove B, A is the only one left, and it's still connected, and the connectivity is 1 because there's only one cut vertex. If we remove the last cut vertex, then we have 2 independent graphs, which we can call B1 and B2.
So let's say we have a graph tree that's not n plus 1 regular, where n is the maximum degree the graph G has. G is connected and also has a spanning tree. Let's say the root of this graph G has a vertex named x1 or v. So all of its connected vertices has the names of x2, x3, x4, x5, and so on, all the way up to x of n, where x of n is the last vertex x of 1 is connected to. We can say that all the degrees of the vertices x of 1 is connected to has a smaller degree than x of 1. Therefore, we can say that each of these vertices can uniquely have its own color, for example, red, blue, green, or striped, and so on. So that by the time you get to x of n, there is still at least one more color that you can color x of 1, the original root vertex, such that the total number of unique colors is at most n, or the maximum degree.
So in Laval's proof, he considered graph G as a non-n-regular graph and an n-regular graph. When graph G is an n-regular graph, he divided 2 situations when G has a cut vertex and when G doesn't have a cut vertex.
This is a case where we have an n-regular graph, where n equals 3. And the reason why it's n-regular is because every vertex has degree 3. Let's say if we were to take out one cut vertex, either the black one or the brown one in the middle, then we would have 2 separate graphs and the coloring wouldn't change at all. If I were to add a vertex so that I could connect the 2 graphs again, then I would make 3 edges coming from that vertex, and that vertex would be black again.
So the second situation is G does not have a cut vertex. Here is an example. So first, let's find the point x in the graph G so that point x is adjacent to not all the other points but has a degree of at least 3. If the graph G without point x is still 2 connected, which means it does not have a cut vertex, so let A be the point x and B can be any points at the distance 2 from point x. So here's another example when G without the vertex x is separable, which means it has a cut vertex. So for example, here is a point of x in the graph G. When we get rid of this point, graph G is like this, and here is a cut vertex. And here is another cut vertex in the graph G. So take this cut vertex as an example. So G minus x is separable. We can mark 2 n blocks in graph G named B1 and B2. According to the definition of n blocks, B1 and B2 must contain a point Z such that Z is the only common vertex of B1 and B2, which is also the cut vertex of these 2 n blocks. Thus, we can always find A belongs to B1 minus Z and B belongs to B2 minus Z adjacent to X. Here is an example of graph G. It contains 2 points A and B at distance of 2 such that G minus A minus B is still connected and X is a point adjacent to A and B. As the same situation before, we can arrange its points in a sequence x1 equals x, x2 until xn such that each point xi is adjacent to an earlier point. Let A and B get the same color 1 since they are not adjacent to each other. Then, as we did before, according to the greedy algorithm coloring, we can successfully color those points. Then, as we did before, according to the greedy algorithm coloring, we can successfully color those points.
Oh, I get it. I get Brooks' theorem now.
I'm glad you did, kiddo.
Thanks, Brooks.